Hi, my name is Michelle, and I'm here to tell you about the O2 analyzer, or also known as a sensor. So what is an O2 analyzer? The O2 analyzer is basically a medical device that is used in various equipment, usually respiratory, and it measures the percent of O2 that is delivered. How does it work? Basically, it works by a chemical reaction that occurs between such chemicals like potassium hydroxide and oxygen. This reaction creates an electronic potential. The sensor contains a cell with electrodes. When O2 comes in contact with that cell, the potential developed will be proportionate to the O2 concentration. The cell is called an electrogalvanic fuel cell. The electrogalvanic fuel cell works by consuming O2 as the cell oxidizes. When the fuel is used up, the chemical reaction ceases and the electrical potential will drop to zero. When this happens, the cell needs to be replaced. When you get your new O2 analyzer cell, it comes in these little airtight containers that kind of look like cat food cans. This is some from work I had. The one on the right is sealed, and obviously the one on the left is open, so you can see what it looks like when you open it. This is basically an electronic schematic of the O2 analyzer. Basically, it just kind of shows you how it works from an electrical point of view. And I did find this video that where a guy compares the oxygen sensor to a battery, and I thought it was interesting, so I will play it.
So what does a battery, a potato, and an oxygen sensor have in common? They might be more similar than you think. We're all familiar with batteries. We've got them around our house, plugged into all kinds of different devices. And in high school science class, you may have taken a potato, some nails, some copper wire, and lit up a little LED, turning this into a battery. Did you know that oxygen sensors perform in virtually exactly the same way? Let's take a look. So to help us better understand oxygen sensors, it's actually helpful to talk about batteries for just a second. So like batteries, they come in all different shapes and sizes. So we've got little batteries and big batteries for different applications. There's different sizes of oxygen sensors for different applications. They have different forms to fit in different types of devices. They have different types of connectors depending on what they're being installed in. And if we look at the inside of a battery, there is a cathode and an anode inside of electrolyte. And what that's allowing happen is electrons are flowing from the cathode to the anode. And when this is connected to a device, it completes that circuit and allows for the flow of electrons. An oxygen sensor is doing almost exactly the same thing, but with a couple of twists. So one of those is that the cathode and anode, the electron flow is actually in reverse. So it's going from the anode to the cathode. And the main thing that's different is that an oxygen sensor, that electrical rate actually changes in the presence of oxygen. So as the percentage of oxygen increases around an oxygen sensor, that voltage will increase. That voltage increase is very linear and very measurable. So you can detect the amount of oxygen in an environment to a high degree of accuracy using one of our sensors. Measuring the amount of oxygen in an environment is important, especially in the medical world, where having too little or too much oxygen can have consequences. For example, the AARC guidelines recommend that all blended gas is analyzed. MaxTech has more than 20 years of experience manufacturing oxygen sensors for customers all over the world. To learn more, visit maxtech.com/sensors.
Okay. All right, here is an oxygen fuel cell dissected. In the upper left-hand corner here, you can see that's the actual housing. And below, it's been taken apart. We have different pieces. There's O-rings, and there's even a circuit board that's involved in this process. Here's the actual cell that's been dissected. As you can see, there's a lot of oxidation around this, so it probably needs to be replaced. Here's a video I made of just kind of simply putting the cell and the housing together with the oxygen analyzer.
Okay, here is a oxygen analyzer I borrowed from a biomed shop. And here's the cord. This is the housing. You can kind of see the metal in there. This is the housing that houses the fuel cell. Let me just kind of put it on the end like this, screw it in. And this end goes into whatever oxygen device you're going to use. And let's say this is your oxygen device. And this kind of screws on the end there. So this goes in line with some kind of various respiratory equipment. And that's how it works. And that's how it connects.
All right.
Okay.
Okay, so who invented the O2 analyzer? In the late 1940s, a chemist named Linus C. Pauling came up with a way to measure O2 contained in closed environments. That's him on the left there. He discovered O2 is attracted to magnetic fields. Pauling and his staff used this property known as paramagnetic property to make a device that used magnets that measured the O2 concentration in air samples. He got help from another chemist, Arnold O. Beckman, PhD, who designed the first O2 analyzer for him. That's him on the right. This happened here in the US. Dr. Beckman is also known for the invention of the DU spectrometer and the electronic pH meter. So he's done a lot of stuff. Here is some original O2 analyzers, the Beckman oxygen analyzer from 1956. The first oxygen sensors were used in airplanes and submarines to measure the O2 levels, but then later on they were used widely in hospitals and other settings. The first one that was used in a clinical setting was in a hospital in Pasadena, California, for an anesthesiologist who had a granddaughter who was born prematurely. It was used in her incubator, and by the late 1950s, O2 analyzers were used most commonly in incubators. And here's a picture of an incubator with a baby. Here's some more early versions of the Beckman O2 analyzer. These are from the 1950s. Here's some 1960s to 1980s models. You'll notice they're usually run on analog. Here's some O2 analyzers from the 1990s. The bottom two are from the early 90s, and the upper two are from the later 90s, and they went digital. There's not much difference between the ones from the 1990s and today, so they haven't really changed much in the last 25 years. So why is it important to monitor O2? Well, some of the patients in the hospital have certain things that where oxygen needs to be monitored, such as COPD, chronic obstructive pulmonary disease. These individuals have a lung disease where they retain CO2, and when you give them too much oxygen, they retain even more CO2. This is bad for their blood pH levels, and it can also make them a little loopy, so we kind of want to keep their oxygen on the lower end of the percentage. Neonates born under 35 weeks, they are at risk for retinopathy of prematurity. Basically, that's a disorder that can make them blind if we give them too much oxygen, or it can make them just have eye issues in general. So we want to monitor their oxygen levels. And also with the coronavirus, I know over the summer, especially with the Delta variant, our O2 concentrator for the hospital was really overworked. So they had to make an exception and have the people with the COVID have a saturation of 88 or greater. Usually it's 92 or greater. So our O2 system wasn't overwhelmed. Where can you find O2 sensors? Well, anywhere there's equipment, respiratory equipment, which is pretty much ICU, NICU, patient floors, OR, any place like that in the hospital, pretty much everywhere. Going from left to right, we have some basic equipment you can find it in. Starting from the left, there's a BiPAP machine, and then we go to a high flow nasal cannula. That's pretty popular with the COVID patients and the neonates. Next, we have a bubble CPAP device, and you can kind of see the O2 analyzer at the top there. And then, of course, at the end, there's a ventilator. So I'm going to show you a video of how to calibrate a basic handheld O2 analyzer.
Okay, here we have an O2 sensor to room air. I'm going to turn it on. We'll make that noise. We unlock it. To calibrate it, we push the triangle. And it's 20.9, so it checks out.
Okay. Ventilators and BiPAPs, we don't usually calibrate the O2 sensors in those because they usually have pre-checks we do, and it will automatically calibrate the O2 sensor in that check. Here's a video with the Vivo 55. It's a little bit of a smaller ventilator, and it kind of shows you how it works within the vent system.
So in this video, we're going to cover the setup of the FiO2 sensor. So the FiO2 sensor allows you to measure the fraction of inspired oxygen that you're delivering to the patient from when you're entraining the oxygen through the device. So the FiO2 sensor comes in 3 parts. You have the T-piece adapter, the actual FiO2, the oxygen sensor itself, and then the cable as well to connect all 3. So when you first get them to put them together, put the sensor into the top of the T-piece like that. The cable then goes into the top here. The T-piece then connects to the patient outlet there, and then we attach the sensor cable into the FiO2 socket on the side of the device. So the end of the cable is colored white here, and it lines up then with the white outlet on the side of the Vivo 55, so you know which one to plug in. So once you've got the FiO2 sensor set up and connected, you'll first need to calibrate the sensor. Your medical physics department may do this for you already. You will need some oxygen entrained through the device in order to be able to perform the calibration. So first you'll need to switch on the ventilator. Just push that on, one push of the button on the side. And to access the calibration in the menu, we want the others menu. Push that button once. We can then scroll down with the down arrows until we get to FiO2/CO2 calibration. Then want to push the arrow to select that, and the device will then take you through the step-by-step process of how to do that. Once the FiO2 sensor has been set up and is ready to use, it will tell you the fraction of inspired oxygen on the screen when the ventilator is running. The sensor module on the side here will need changing roughly every 6 months. One thing that's important to note when entraining oxygen through the Vivo 55 is that you should only be entraining oxygen while the device is actually running and ventilating. So make sure that you start the treatment first on the ventilator, then turn on your oxygen. When you want to stop treatment, turn off the oxygen before stopping treatment on the ventilator. In summary, we've just covered how to set up the FiO2 sensor, so you'll now be able to monitor what the fraction of inspired oxygen is that you're delivering to your patients.
All right. So how often should you calibrate your O2 analyzer? According to Precision Medical's catalog, they recommend when your O2 is set at 100% and your sensor is reading below 97 or above 100, it should be calibrated. Or if the cal reminder icon, it's usually a triangle, is displayed or flashing, that usually means the machine needs to be calibrated. Or if you're just unsure about the O2 displayed. Maintenance, make sure it's disconnected before you clean. Use a damp cloth, mild detergent, make sure it's dry, and wipe your O2 sensor and diverter with a dry, clean cloth. Another thing to note is that humidity over 95% can also affect the O2 sensor. So we probably don't want to leave it outside in the middle of summer in Florida. Now, different companies and prices. Max Tech, they seem to be the main company that makes these. And there's other ones too. I know Precision Medical, like the one I had, was displayed there. They range in price from about $100 to $1,000, depending on what type you need. These are just some examples. They are class 2 devices. A class 2 device is basically a device with a moderate to high risk that requires special controls. It's not as life-threatening as a ventilator, which supports the lungs, but there is still kind of important, so they put it in class 2. Of course, with the patients I mentioned, it would be important. Recalls. 2 recalls I found were the Cooper surgical oxygen sensor and the Teledyne portable oxygen analyzer. The Cooper one had an issue where it had you'd set an oxygen and an external analyzer was reading 3 to 12% above or below the actual what it should be, and it would not alarm, so they pulled that one. And then the Teledyne one had it's supposed to have a light that lights up when your batteries are low. And that wasn't working, so they had to pull that one. And also, I forgot to mention, oxygen analyzers usually run on batteries, especially the handheld ones, and they're usually AA's. And that concludes my presentation. I hope you enjoyed it.